Dr. Alexander Karakovsky, Mathematics Department Chair.
Welcome to Mathematics Department Graduation Ceremony. My name is Alexander Karakovsky, and I have the privilege of serving as the Chair of Mathematics. Today is a very special time when we recognize our graduates. All of us know that getting to this point required an enormous amount of work, tremendous dedication, motivation, and ability to overcome many difficulties in your path. This year's epidemic presented a unique set of challenges. I am very proud of all of you for persevering despite the abrupt and sudden change. This past few months hadn't been easy for anyone. I am very sorry that we can't get together to celebrate and honor your wonderful achievement. Luckily, the technology allows me to offer all of you my heartfelt congratulations. We are happy that you made this great choice to study mathematics. Math and logic skills that you acquired during your studies will serve you well, whether you decide to go in academia, industry, or choose a career in a seemingly unrelated field like medicine. Indeed, many mathematicians and statisticians currently are working around the clock to help governments at every level to make better decisions in these difficult circumstances. We hope that you will spread the message about the vital importance of mathematics wherever you go. This is also a moment to reflect on all the people who helped you along the way. Parents and family members, classmates and teachers at school, and your CU professors and classmates. All the people who rose to the occasion and helped you to do your best and to complete your studies under these difficult circumstances. In the years you have spent here, you became an integral part of our department, and you will always remain one. I would like to congratulate you again and wish you success in all your future endeavors. Stay safe, and I'm looking forward to the day when we can all meet in person to celebrate your achievement.
Dr. Kent Goodrich, CU Boulder Mathematics Professor Emeritus and Keynote Speaker.
Good morning. My name is Kent Goodrich. I'm a Professor Emeritus at the University of Colorado here in Boulder. I taught 44 and a half years in the Mathematics Department. I appreciate the Math Department inviting me to address the class of 2020 because there are two things dear to my heart, mathematics itself and mathematics students. So, start off by saying congratulations to the class of 2020. It's been a tough semester and you've made it. So congratulations. It's a real achievement. And it's also a very happy, glorious day. Except, as we know, we are the subject of a relentless and cruel virus that has emptied the campus. I just walked across it. It's still as beautiful as ever, but it's empty. It's lost its heart. And so that's very sad. It's hard to see. But we have to remember, even though we're in the middle of a pandemic that's affecting the entire world, our nation, this campus, and each of us as individuals, still good things happen even in a pandemic. In the year 1665, Isaac Newton was a student at Trinity College. He bailed out. He went to the country farm. And during that year and the next year, he really advanced calculus and physics. Very productive time for him. So you got to remember, even in a pandemic, good things happen. Today, people are having babies, people are getting married, and yes, students are graduating. So this is something to celebrate. Now, it's probably a good idea to reflect on how you got here. A lot of people have helped you get to this point. Your parents, most likely, or family, extended family, all your teachers from grade school, middle school, high school, they prepared you to come here, study at the university. And it's been successful, obviously. Also, everybody in the university has helped you. Staff, tutors, graduate students, graduate teaching assistants, instructors, regular faculty. So I would point out to the class of 2020, it's not a bad idea to sometimes thank some of these people. It means the world to them to hear thanks. It really does. So you might think about that. Oh, I left off one. Your thesis advisor, if you're getting a PhD. They really have a lot to do with you getting that PhD. So what is it have you learned? Well, I was at a conference once, and then Governor Roy Romer said to me, it's very hard to say what a student got out of their college education. It's hard to quantize that, and hard to know how much they learned. I told him that wasn't true in mathematics. I think I know a lot what you've learned. You're probably today a much better problem solver than you were several years ago. You're also better at attention to detail. So that's something that you have learned. And you can think better. You're more articulate as far as expressing mathematical ideas to other people. And that's important because people have trouble understanding mathematics. So it's good to be able to articulate these things. So this sort of starts with the first thing you learned is logical thinking. Now, Edgar Allan Poe, a writer, said, the steps towards calculus are sometimes missing. These stepping stones are missing, and that makes calculus unnecessarily hard. I think what Poe was talking about was what we call prerequisites. You have to learn these prerequisites before you can move on, and they pile up. As you go along, there's more and more of them, more information that you have to know to go further. I sort of look at them as stepping stones, as Poe did. You're like trying to cross some water, and here are these stepping stones to step on. Students have learned to break a big problem into little problems, solve the little problems, and then put them back together. That's these stepping stones. You have to be able to go from one to another, one by one, building up, using logic, using other stepping stones that have been established before. Now, what are these? Well, in Poe's case, he probably didn't know enough trigonometry or algebra. But those were the stepping stones. You break this problem into little problems and solve each one. Well, what are those little problems? Nobody tells you what they are. You have to know what they are. You have to either know them or invent them. Now, what they are, for us, if you think about just a normal calculation, each step in the calculation is justified by some mathematical rule or axiom. We don't usually list those out to the side of the calculation, because that would make it look ugly. But they're there, and they're there for a backup. And so even an ordinary calculation uses these stepping stones, one by one. So you think, well, that's pretty mechanical, and some of it is. Mathematica, which is a computer program, would probably get a C in my calculus class at the end of my career, because it could do calculations and it could do all sorts of formulas and manipulate them like a human, but it couldn't invent a new stepping stone. That's what makes it interesting. When there's a new stepping stone, where does that come from? Out of somebody's head. But it's only coming after they've learned this whole big infrastructure. They know a lot of previous stepping stones that were provided by earlier mathematicians, earlier people, and now it builds up. It builds up like a giant network or a giant spider web. And so now you're saying, I'm going to put another stepping stone over here. Well, where did that stepping stone come from? It's out of the human mind. So far, computers aren't too good at that, fortunately. It keeps us mathematicians going. But somebody has to write the code, even for Mathematica, to do these calculations. That's the creative part, building this, proposing another stepping stone, and then making a path to it of small steps till you go from the known infrastructure, the known results to this new result. That's what our PhD students just did. 9 of them. That's an amazing production for a small math department, 9. They had 9 last year, too. And so I congratulate the math department for this high productivity. It's even higher than 20 years ago when we had more faculty. So I think that's a real tribute to them to be able to do that. So anyway, back to this big network. Students know how to navigate this network because they've learned more and more of these steps, more and more of the spider web, more and more of the network. They might forget some of the pieces of this network, but they don't forget that idea that you break the problem into little problems, solve each little problem, and put it back together. That's how you get to a new stepping stone, or to a stepping stone you might want to apply or use in an application. Now, I'm reminded, I had a student who had been out of school for a while. She decided to go back to graduate school. Well, she came back. It was very hard. She was getting kicked around. She said, Professor Goodrich, I'd forgotten my trig, I'd forgotten my calculus, but I hadn't forgotten how to think. She knew how to string together these arguments. She knew this structure, the logic behind it. That stays with you long after you've forgotten all the formulas, all of the theorems, all of the axioms. You'll still have that ability, and that's an important ability in the world. It really is. Okay, so logical thinking and being able to express yourself mathematically are all important. And so I think Governor Romer was wrong when he said it's hard to quantify that. It's not hard to quantify, in mathematics anyway. Maybe in some other fields it is. Now, the second thing you've learned is you've learned how to learn. Now, that sounds kind of weird, but it's not straightforward. Learning how to learn, you've got to know something to learn about. And mathematics is good that way. It's huge. Nobody understands this whole spider web. Nobody. Used to be back in Newton's day, maybe you could understand most of it. Now, it's impossible. One person just doesn't have the mental capacity to absorb all of that. Learning how to learn on your own is a priceless skill. I would encourage you to learn something new every year of your life. It adds up. Believe me, it adds up, and it's worth doing. In fact, right now, where things are kind of slow maybe, it might be a good time to learn something new. And you gain the confidence that you can learn something by learning mathematics. It's difficult enough that you have to push yourself and not get too discouraged because it takes a long time. It takes a long time to get there. Okay, so that sort of gives you a little strange idea of what mathematicians do. They build this big web of information, one step at a time. It starts back with what we call the axioms. These are our solid foundations that hold it together. And those lead to the rest of the web, the rest of this spider web. Well, what's interesting is the spider web, a lot of it was built before the axioms. It was only in the last century that these axioms came to the fore and were made understandable and useful. So it's funny because you had this big structure sitting out here with nothing supporting it. It was lucky it didn't collapse. Parts of it kind of did for a while. People lost confidence in calculus because sometimes it would work, sometimes it didn't work. They didn't know why, but they do know that now. And so students didn't have to go through those machinations. Okay, so that's, I think, the two things you've learned. Logical thinking and learning how to learn. Those are the two things that will stay with you for life, whether you use your mathematics education in any other way. Well, what do our students do after learning this? Well, a lot of them go on to graduate school. Most noticeable group are the ones that go to graduate school in mathematics. They're the ones that are going to create and add these new stepping stones out on the boundary of knowledge and maybe teach themselves, because that's one fairly substantial group. But then we find out a lot of our students go into graduate school in other fields besides mathematics. That's because we lead the university in double majors. The math department produces more double majors than anybody else. And I think part of that is because mathematics is at the foundation of most of the sciences and engineering. So that's why they can go to a graduate school in some other field besides mathematics with the math degrees, because they double majored. So a lot of them do that. A lot of them are double majors. They go to graduate school in engineering fields and physics, for example. We have a lot of physics double majors. Then there's a lot of students that go on that don't really use their mathematical training except for the logic, except for the reasoning power and the communication skills they've learned. Such as we have students go to medical school. We have students go to law school from here. It's a good preparation. It impresses the committees that say, wow, they were able to learn mathematics. They can't be a total slouch. You know, they learned something hard. So many of our students will become software engineers. The computing industry and software development has an insatiable appetite for our students. It's insatiable. I once predicted that the need would never be met, not even close. But I didn't figure on China and India coming into the picture and producing a lot of software engineers. That changed things. It really did. So my prediction, it might be a little tight sometimes, but it's really a huge industry. And what happened was a lot more of society has been subjected to mathematical analysis now. Why? Cheap computers. Cheap computers made this possible. This would not be happening without cheap computers. So we have to give the electrical engineers a tip of the hat, and mathematicians help develop the computer, though, so they can give a tip of the hat back, I hope. Okay, so a lot of software engineers. Another big field that they go to is actuarial work, which is the mathematics behind the insurance industry. We have a certificate program here in the department with some other departments on campus, including applied math, that produces actuaries, beginning actuaries, we should call them. And our students have been very successful in that. They do very well in the national exams. Then we have, some will go to Wall Street. A lot of them are working on models, mathematical models of things like, what's the market going to do? What's it going to do tomorrow? What's it going to do in a week? What's it going to look like in 10 years? So mathematical modeling has taken over. So prediction the outcome of the stock market is big. Weather prediction is big. Used to be you couldn't predict the weather. I remember Richardson said, someday computers will be fast enough they can compute the weather faster than it happens. In his day, they could compute the weather for 2 days ago and say, oh, it was right. Well, not too interesting, but it showed it was possible. And now you get these predictions just all the time. You know, whip out your phone, look at what's going to be tomorrow. And they are so much more accurate than when they started. It's amazing. And then there's artificial intelligence. One of our students is head of a group that's making cars that will drive themselves. And in some cases, that might be a good thing, like myself, if I were replaced by a machine. But I don't quite have the confidence in that yet. But that's artificial intelligence. And we had another student who was kind of a pioneer in that. She made a big name for herself in artificial intelligence and also big data, which is using massive amounts of data to go through it and look for patterns. I guess one of the applications they're thinking about now is tracing who did you go see when you had the virus? Who did you come in contact with using phones? Right now they use it, you're driving down the road, it says, hey, this road over here is busy. How does it know that? It's tracing your phones. Maybe not you personally, but it's tracing the phone traffic. So it knows it's busy there. And then another thing is that this builds a big network of weather data too, because people will say what the weather is at their place. So it augments the data set for the United States prediction. So it's much more accurate than it used to be. It's not perfect, never will be. The weather's too complicated. We mathematicians know that. So we have all these people that have finished. One that has probably nothing to do with mathematics, but is interesting. One of our students is the co-creator of the long-running TV series South Park. And it'd be nice to get him and come and give a talk sometime. We invited him, but I think he was too busy writing more scripts. So, but that's interesting that we had somebody like that. We have a co-founder of Oracle, which is a huge software company. We have two of our students became distinguished professors at some other large universities. One student took third 3 times in a row on a national crossword puzzle competition. And you say, well, gee, where would a guy like that end up? Well, NSA, National Security Agency. It's the largest employer of mathematicians in the world. And what do these people do? Well, they keep our code safe, hopefully, and they break the other guy's code. So we're reading their secrets sometimes. So they hire a lot of mathematicians because mathematics has turned out to be useful in that endeavor. Now I'd like to make a few personal remarks. I taught at the university for 44 and a half years. During that time, I saw some remarkable things. Humanity went to the moon. That was something when I was a child nobody thought was possible. But humanity did that. I saw physics and cosmology undergo huge revolutions. The study of the very small, atomic structure, and the very large, the cosmos. They've made a lot of progress on both, but what's interesting, the more progress they make, the more confusing it gets and the less certainty there is. So there's going to be another revolution coming up in physics. I might not live to see it, but maybe the class of 2020 will see it. We hope so. But, and then I saw a lot of famous mathematical problems solved. I used to give a talk to high schools stating some unsolved mathematical problems. And the list got shorter and shorter as my career went on. So there aren't too many of those left. But that was remarkable too. So it's been very gratifying watching that progress and doing research. And Hardy said, said something like, couldn't find the actual quote, everybody wants an intellectual kick. And there's no better kick than mathematics. I believe that. And our graduate students really know that. Now, so that was all very gratifying, doing my own research. But it really wasn't what made me tick. It wasn't really the most gratifying part of my job. What that was watching the light go on in the face of a student when they finally understand a difficult concept or solve a difficult problem. The light goes on, and they see it. It's like a little miracle. It really is. Every time it happens, it never gets old. It's a miracle. Nobody knows how it happens. I don't know. How do they finally see it? Or how do, as a mathematician, finally see this thing out here on the edge? Nobody knows. That's part of the mystery of mathematics and part of the beauty. You know, these paths I was talking about, sometimes you're composing them. You're not just constructing them, you're composing them. It's a little like music. And the interesting thing about our double majors, I think the second largest group is music. So there's some weird connection between, maybe not weird, there's some connection between music and mathematics. I don't know what that is either. I don't have it, so it's hard for me to say. But there is an interesting connection there. Okay, so it's been fun watching these students grow. There's nothing quite like it. It's wonderful. It's the most gratifying part of my job, watching them learn and grow. And one more thing I'll say about this sudden flash of insight. It doesn't happen without hard work and learning this big network. It just doesn't happen. Okay. Now, I know these are trying times, and I'm sure the job market has been disrupted. But I think brighter days are ahead of us for this class, 2020. Medical and biological sciences have solved some very wicked diseases, some very relentless and cruel diseases. Polio, for one, and measles. All sorts of very communicable diseases have been solved by this science. These scientists will solve this virus. Nobody knows when, but they will. They'll get it. The university will reopen. The classes will fill with students eager to learn again. The seminar rooms will fill up. Basketball games and football games will resume. And yes, spring graduation will resume. I see it now. There's going to be Math 100 full of proud and happy students. The sky is going to be blue like it is today. The dark blue of Colorado, dark blue sky of Colorado. It's beautiful. The staff will put together a wonderful celebration. I've been to more than 40 of these in my career. They're wonderful. It's like being Santa Claus. You get to see these kids so happy and their parents so happy. And that's one sorrowful thing, that you didn't get to experience that. Now, I understand the university said it's okay for you to come to Next Springs. Is that right? Yeah, yes. So if you want to have this experience, it's once in a lifetime. It's worth doing. Now, when I was a student, I wasn't wild about it, but my parents were. Your parents would be too. See you walk across the stage and get your name read, and your handshake with the chair of the department, and take pictures with your student and some of their faculty. It's worth doing. Well, we don't know when that's going to happen, but it will happen. This will happen. In the meantime, be patient, be careful, and protect all those near and dear to you. And if you're bored, looking for something to do, learn something new. This might be a time, an opportunity, just like Newton, to learn, even if you don't create calculus, learn something new. Add to your knowledge of this giant web that's building so, so fast, nobody can keep up with it. So I'll end with one more. Congratulations.
Dr. Sergei Kuznetsov, Mathematics Graduate Chair.
On behalf of the Math Department, I would like to congratulate our graduate students who obtained their PhD during this academic year. We have 12 of them. 2 of them actually graduated in the fall, but still we have to congratulate them now. So let me name them. Yeah, so the best and the only possible is to use alphabetic ordering. So the first is Catherine Adamick, and she was a student of Professor Boulder, and she did her PhD devoted to classification of Q0 local A1 modules. Don't ask me what is that. Next is Sebastian Bosley, a student of Professor Weiss, who did his research on application of logarithmic geometry to modeling of curves of genus greater than 1. Andrew Healy, a student of Professor Karakovsky, who did his research in explicit quasi-isomorphism between the causal and bar resolutions of Weyl algebras. Trevor Jack, a student of Professor Meyer, computation complexity of semi-group properties. Said Khalili, my student, who did his PhD on stochastic analysis for problems in mathematical finance and economics. Taylor Klotz, a student of Professor Cleveland, who did his research on geometry of cascade feedback, linearizable control systems. Daniel Martin, a student of Professor Stench, who did his research on geometry of imaginary quadratic fields. Caroline Matson, a student of Professor Grant, who did her research on multidimensional formal group laws with complex multiplication. Mark Pullins, a student of Professor Kearns, generically to transitive algebraic group actions with solvable points of stabilizers. Hanson Smith, a student of Professor Stench, who did his research on monogeneity and torsion. Athena Sparks, a student of Professor Meyer, colonoids and promise constraint satisfaction problems. And finally, Zhenhua Wang, a student of Professor Englander, who did his research on random processes and stochastic controls. So we are really proud of you. We are actually proud that you have chosen us to do your research. We will definitely miss you for It was really a great time when you were doing your graduate studies with us, and we wish you all the best in the future. Thank you.
Catherine Lauren Marie Adamick, PhD.
Hello, everybody. Today, I'm extremely proud to present to you Dr. Adamick. She defended her thesis in April. She's my very first student to finish her PhD, so I'm really, really proud of being here with her today. So let me tell you a little bit about her research. All right, so first I'm going to tell you about some of the words that are in the slide. So Dr. Adamick's field of study is algebraic topology. So this is an area of mathematics which uses algebraic structures, so algebra, to simplify questions about complicated geometric things, so the topology in algebraic topology. So what are algebras? Algebras are collections of operations that are like the symmetries of geometric objects. So we use these algebras to study geometric questions that are hard to approach from a purely geometric point of view. So these algebras, they have attached to them something that we mathematicians call modules. So the modules are things that have a multiplication by the operations of the algebra. So Dr. Adamick studies the Steenrod algebra specifically. So the Steenrod algebra is one of the central tools that algebraic topologists, like Dr. Adamick, use to better understand complicated geometric objects. So the Steenrod algebra itself, it has smaller pieces that we call subalgebras. And understanding the small pieces can lead to a better understanding of the whole. So in her thesis, Dr. Adamick focused on a small piece of the Steenrod algebra called A1. Specifically, she completely classified a certain class of modules over A1 that we call Q-naught local modules. Her work has consequences for understanding the Steenrod algebra itself and its modules, and it feeds into important and powerful computational tools that many of us algebraic topologists love to use. So that's all I wanted to say about her research. If you have questions or want to know more, I'm sure that she'll be very happy to talk to you. However, in her graduate studies, Dr. Adamick didn't only do math. She's been very outdoorsy. She's been hiking and she picked up kayaking. She's also been working with the CU Graduate Student Labor Union. In particular, she's been fighting to get rid of student fees and to improve graduate student compensation. So this is very important work, and I'm really, really proud of Catherine for being involved in this. Finally, she loves to knit and knit really awesome things like this nice sweater. Looks complicated. I don't think I could have done that. Yeah, so finally, before we finish this little video, I want to present to you Dr. Adamick, and she's going to tell us what's next for her.
So moving forward, I'm really excited to continue some collaborations that I was able to start in graduate school. Here's a picture of a group of some of us who are going to be talking about math this summer and moving forward. And then I'm going to be moving to London, Ontario to start a postdoctoral position at the University of Western Ontario, which I'm really excited about.
One last time, I present to you Dr. Adamick.
Sebastian Bosley, PhD.
Hi everyone, I'm Jonathan and this is my student Sebastian Bosley. His thesis was titled An Application of Logarithmic Geometry to Moduli of Curves of Genus Greater than 1. So you can see Sebastian there on the right. He's wearing a hat that he often wore to our meetings. He didn't always wear the suit, though I've seen it before, and I won't tell you how often he brought a bottle of wine. If I could describe Sebastian in our meetings in just a few words, I think he was always very well prepared and always very precise when he wanted to explain something on the board. He scarcely ever made a mistake. And that kept us always making forward progress, and I led to the great thesis that I'll tell you about in just a second. Also, he had just beautiful handwriting. He studied algebraic curves. Those are curves over the complex numbers. Now, the complex numbers are two-dimensional, so when we talk about a complex curve, usually you want to visualize that as a surface. And the question that he studied was, what happens when you take that surface and you stretch it, you deform it, so that it stretches out? What does it have some limit as you stretch it out? We know that limits exist, and it turns out there are lots of different limits for just one way of stretching. And the question Sebastian was asking was, can we classify those limits? Can we construct them in some kind of systematic way? So the way Sebastian did that was to look at the nicest possible limit. That was discovered about 50 years ago, and it's a limit that has only nodes as singularities, the simplest kind of singularities. He drew a stick figure picture of those nodes, and you can see a diagram of a whole bunch of those stick figures on the right side of the picture on his slide. And the question he asked was, can we decorate the stick figure with some extra information to construct some other kinds of limits? So Sebastian came up with the idea of a mesa. That's a way of assigning heights to different parts of that stick figure. And out of those heights, he was able, by an absolutely ingenious and difficult procedure, to replace the parts where that mesa is high with some kind of complicated singularity. It's a very clever construction. And it's given us a lot of new ways of constructing these limits. Right now, we don't even know how many new ways there are. We know there are lots. And we have a summer research project running right now with 6 graduate and undergraduate students trying to find as many of these limits as we can. Sebastian, when he defended his PhD successfully, he celebrated by buying himself a microscope. So he's got a picture of his pinky finger there on this slide. I guess Sebastian wanted to give you just enough information to steal his identity. If you want to, you can copy his fingerprint, and on the left you can see exactly where he lives. Next year, Sebastian is going to be a postdoc at Tufts University. He'll be working with David Smythe. David is one of the world's experts in this question of finding limits of curves as they're stretched out. And I think he and Sebastian are going to produce some really exciting work together. Please join me in congratulating Dr. Sebastian Botzley.
Andrew Scott Healy, PhD. Trevor Jack, PhD.
Hello, it's my pleasure to introduce Trevor Jack and his PhD dissertation on the computational complexity of semigroup properties. Just for a bit of background, remember that composition of functions is associative. So if you're given a set of functions, or even partial functions on a set, the composition form an algebraic structure that's called a semigroup. Similarly, a set of matrices, square matrices, forms a semigroup under multiplication. Now, what Trevor did for his PhD thesis was designing and analyzing algorithms for computations with these semigroups given by functions or matrices. In particular, he considered questions like, given a set of matrices or given a set of functions or partial functions, how hard is it to determine whether the semigroup that they generate satisfies certain properties? So the properties that he considered, you can see in this table on the left. And the complexity classes for various cases you see on the table, for functions in general, for matrices, and for partial bijections over here. So for example, given a semigroup of functions, how hard is it to determine whether the semigroup is nilpotent? It can be done in non-deterministic logarithmic space for functions. For matrices, matrix semigroups is supposedly a bit harder, but still can be done in polynomial time. And so there are a lot of results here. Before Trevor's work, not much was known about the exact complexity of these computational problems, but he really obtained a lot of results on which computations are easy and which are hard for semigroups. Besides working on his PhD for the last 3 years, he also followed some other pursuits, like going rafting, skiing a lot, playing music with his band. I've never heard that, but there's a photo to show it. What's next? Trevor is going to start a postdoc at Universidade Nova de Lisboa in Lisbon, Portugal next fall. There he'll work within a research group on more computations on more semigroups. That's it for the presentation. Trevor, I dubbed the talk to Jack. Congratulations to your PhD and all the best for the future.
Great, thank you very much. I'd like to thank my advisor here for all his wonderful advice, my friends and family for their love and support, and I look forward to my next adventure in Portugal. Hopefully, fate brings me back to Boulder at some point.
Saeed Khalili, PhD. Taylor Joseph Klotz, PhD. Daniel Everett Martin, PhD. Caroline Liggett Matson, PhD. Mark Pullins, PhD. Tyler Schrock, PhD.
Tyler Schrock was a PhD student who graduated in December of 2019 and was working with myself and Raf Frangillo. His dissertation title was On the Complexity of Isomorphism in Finite Group Theory and Symbolic Dynamics. He was working with me mostly on the group theory, so I'll talk about that. Groups are essentially the fundamental study of symmetry in mathematics. And if you have two different objects with two different kinds of symmetry or kinds that look different, you can ask, are they secretly the same kind of symmetry? This has been a central problem in computational algebra and computational complexity theory for 40 or 50 years. It goes back all the way to Dane in the early 1900s. And in this chapter of Tyler's thesis, Tyler was tackling some of the hardest cases of this problem. And while the problem at large still remains open, Tyler made some very nice progress on some of these hardest cases.
On the right, so on the other half of his thesis was on symbolic dynamics, which is the study of dynamics on infinite sequences of symbols. And here, one of the core open problems, which has been open for 40 years, also considers isomorphism. It's about conjugacy between two shifts of finite type, which a conjugacy here means isomorphism that respects the dynamics in some sense. And Tyler's work was attacking some special cases that are important building blocks towards the larger conjugacy problem. So unbeknownst to us, Tyler was up to many other things during his PhD, including backpacking and getting some nice air on the snowboard and traveling around. And since January, Tyler has started working at Google in Pittsburgh, and we wish him the best there. And without further ado, the real Dr. Schrock. Congrats, Tyler.
Congrats, Tyler.
Thanks. It was a pleasure working with the two of you.
Hanson William Smith, PhD.
So I'm very pleased to introduce Hanson Smith. I'm very proud to have worked with Hanson. It's been a great pleasure. Hanson has done some excellent work in his thesis, which I'll tell you about in a moment. But besides being a fantastic mathematician, he's also a real member of the mathematical community. So Hanson, for example, is a founder and organizer of Front Range Number Theory Day, which is a new twice-yearly one-day conference to bring together mathematicians in the Front Range. He really cares about mathematics and about sharing mathematics. He has worked with undergraduates, mentoring undergraduates, and high school students. And I look forward to Hanson being a member of the community for many years. So let me tell you a little bit about Hanson's thesis. So he studies what are called number fields. And they're rings of integers. So we're all used to the regular integers, and they live in what's called a field, which is the rational numbers, where you allow division, essentially. In the integers, you can't divide everything, but in the rationals, you can. And he studies some of these rings of integers in number fields, which you can build by adding some more elements into the regular integers and getting a number system which is a little bit bigger. And one of the questions you can ask, a very fundamental question, so he's contributing to research which has gone back hundreds of years, is to ask, how can you build these rings of integers? Can you do it by adding just one extra special number to the regular integers? And if you can, then it's called being monogenic. So there are certain fields where we know the answer to this question, but a lot of the time we don't. We don't know a general criterion for when things are monogenic or not. And he studied some number fields, various different families of number fields. Some of them come from elliptic curves and abelian varieties, which is a very interesting source of interesting number fields. These are, well, they're curves which are defined by polynomial equations, and but they naturally give rise to certain number fields. And he's given some answers to these questions and shown sometimes the answer is yes, sometimes the answer is no as to whether these are monogenic. So that's a little bit about his thesis. Hanson is also an avid climber. I hear about it in meetings, and I'm sure that wherever he's headed, he'll be doing a lot of mathematics. In the near future, his next step is he's going to the University of Connecticut, where he'll be a postdoc. Congratulations, Hanson. I wish you well.
All right, congratulations to Dr. Hanson Smith.
Athena Christine Sparks, PhD. Zhenhua Wang, PhD.
Hi, everybody. Zhenhua was my PhD student, and I was very fortunate having him. And as a matter of fact, I have to admit that when I first met him, I thought that for him, this would be he just needed a formal advisor because he already had another advisor in the applied math department. And to my very pleasant surprise, it turned out that he actually took very seriously the research work with me, besides his other research, which he also took seriously. So I was very fortunate to have him as a student, as a very enthusiastic student, and he wrote a very nice paper with another collaborator, which went to a very good journal, and it was an absolute pleasure to work together with Zhenhua. And I think I can even say a few words about what we did in a kind of a non-technical language. So maybe we should go to the next slide for that. So the left side shows the work with me, and the right side shows his work with Professor Huang. So what he did with me, it's very easy to give a very simple description of the model. You take a coin, and instead of tossing this coin, you always turn it to the other side with a certain probability Pn. So Pn is the probability at time n. And then you can ask all kind of questions about the sequence of heads and tails you get. And mathematically, this is what's called a time inhomogeneous Markov chain. And there is very little known about them. If we turn this coin always with probability 1/2, if Pn is always 1/2, then of course this just reduces to classical coin tossing. And one of the questions in that case, one of the classical questions is, there is you can also look at this as the steps of a random walk, and the question is, what is the scaling limit of the random walk? And there is a classical result which says that the scaling limit is Brownian motion. And so we addressed this problem for a general sequence Pn, and it turned out to be a very rich problem. And the scaling limit of this kind of coin turning walk turns out to be, sometimes it's something which you can derive from Brownian motion. It's something called a random time change of a Brownian motion, and sometimes it's a completely new kind of process, which is a pathwise linear process, which we dubbed the zigzag process. And all these depend on the actual property, the decay rate of Pn, or actually Pn can also tend to 1. If Pn converges to 0, then we say this is a cooling dynamics, and when it converges to 1, we say it's a heating dynamics. And there are all kind of regimes with all kind of different outcomes for the scaling limit. So this is what's represented in the picture. With his other advisor, with Professor Huang, Zhenhua considered a classical problem, the timing consistency problem in optimal stopping. And the basic issue is that when we determine the optimal stopping in a particular problem, let's say in a financial problem, and then we reconsider this problem a little time later, and again we have a certain optimal stopping, there is no guarantee that this second optimal stopping agrees with the first one. So this is the basic inconsistency, and the way to attack this problem is to look for the equilibrium. And Zhenhua and his advisor had results on that regarding the existence of the optimal equilibrium. So that's as much as I can say in a nutshell about it. Of course, this is all motivated by mathematical finance, I would say. I would like to say a few words about what Zhenhua is going to before that. I'm going to say a few words about Zhenhua as a person. So he's a very shy person, and at the beginning he shared very little about himself to me. But after that he opened up, and as you can see, he enjoyed very much Boulder, the beautiful environment here. And also what I had no idea about, he's very much interested in this beautiful stuff in Chinese calligraphy. So maybe you should tell me more about this a little later because I had no idea about that.
Okay. So thank you, Janos, and thank you for your great introduction. And I'm very honored. Okay, so this slides a little is some like personal information about me. So as personal hobby, I like Chinese calligraphy. So sometimes at Boulder, when I'm thinking about questions and also like my research, I may take like relax and just write some Chinese calligraphy on the blackboard, then go back to my research. And
So you
also,
wrote
I also like paintings
on the blackboard. What I can see is all you did then.
It's
on
a
the
poem in
blackboard
Chinese.
yours?
It's a very famous poem. Yes.
And the picture and the writing is also yours.
Yeah. I did. It's a poem from a very very famous Chinese poet called Du Fu. Yes, but I just practice this. Yes, my handwriting. And after came back coming to Boulder, I really like this place. So I start like hiking, skiing, or do some road trips. So Boulder to me is a very very nice place, and I also like people here. People here are also very nice. Yeah. And in the future, I will do a postdoc at University of Michigan Ann Arbor. But I will often come back to Boulder and visit my friend also Janos and Yuri. So at last I want to thank first Janos. He is a really great teacher, mentor, and also a wonderful friend to me that gave me great and valuable advice for both my school life and also academic life. And also I want to thank Yuri for his mentoring and patience for years. He is also a very great, wonderful friend to me. And I also want to thank the big family of Department of Mathematics and for all your support. And also I want to thank my friends and my families. Okay, so I think that's all. Yeah. Thank you all.
Thank you.
Brandon Breeden, Bachelor of Arts and Master of Science. Xiao Liu Chun, Bachelor of Arts and Master of Arts. Dr. Nathaniel Thiem, Mathematics Undergraduate Chair.
Greetings to graduates and their families and friends from the math department. While it generally feels really odd to me to be addressing an assembled graduation crowd, I'm a mathematician and not an orator, this year feels especially strange. But at least I've gained some empathy for late-night hosts surviving without their live audiences. There are a number of things I'm going to truly miss this time around in graduation. I would really like to have seen all our graduates one last time. I really appreciate seeing all of you, even the ones I've never met, but especially those who I've gotten to know over your time here. I will also miss getting to know your families and friends, though that's usually very brief. It always gives me a completer understanding of where you're coming from when I meet the people who've supported you along the way. And finally, I will miss the amazing spread that our department always puts on for these types of occasions. However, I'm also mindful, even though this is a strange year, the strangeness began very recently, and so most of your studies were without COVID-19. And I'm extremely proud of our graduates and their accomplishments, and I have full confidence in their abilities as budding mathematicians. So while not all of you may end up in graduate careers, I expect you will retain the ability to to think about hard problems. You will have learned that many problems do not get cracked with a mere 5 minutes of thought, let alone a month or maybe even a decade, as in the famous example of Fermat's last theorem. I will also expect you to have learned that there are unsolvable problems, even in mathematics. And while they are unsolvable, it is maybe nevertheless useful to be able to think about them deeply. Because by thinking about uncrackable problems, you learn new things and you solve other problems along the way. While the mathematics you encountered here was difficult at times, some of you may remember the third midterm in Calc 2 in particular, you will find that if you do not already know, that real life is even messier and full of even more intractable problems. I hope you will delight in the challenges that await you as you go forward. Congratulations, graduates.
Jarrett Charles Cherry, summa cum laude. Megan Hannah Collins, summa cum laude. Ram Diego Ekstrom, summa cum laude. Henry Charles Fontana, cum laude. Ryan Andrew Mike, summa cum laude. Horamed Nakurt, magna cum laude. Hamad Nawaf Al-Mutwa. Abdul Latif Khalid Al-Abdul Ilalil. Zaid Alfala. Travis Almquist. Munther Algamshi. Ricardo Arosa. Courtney Beckwith. Crossland Joseph Beer. Susan Edith Bourne. Jonathan Micah Bosnick. Nicholas Drew Bossenbrook. Brandon Breeden. Anthony Morel Carroll. Xiao Liu Chun. Alexandra Marie Collard. Clifford Stephen Craw. Connor DePhillips. Guofeng Deng. Kyle Matthew DeGiacomo. Joseph Williams, Director. Natalie Downey. Kyla Michelle Dyer. Justin Thomas Eggers. Adriana Elsa Fabrizio. Riley Griffin Friedman. James William McGinnis Gallmeister. Jason Michael Giblin. Sergei Jataulov. Sheng Gong. Alexa Graffio. Braden Thomas Griebel. Brianna Jo Hagos. Cameron Forrest Hamblin. Devin Jonathan Haw. Marcus Philip Haverhals, Amy Brooke Harmon, Jason Linebier Hoare, Young Peng He, Kevin Charles Hedrick, Darren Kenji Higaki, Yi-Chun Hong, Aaron Song Yu Hong, Siuan Huang, Jeffrey Huyn, Landon Robert Jacquinot, Michael Devin Jara, Shehan Ji, Peng Zhang, Alexander Matthew Kowick, Mark Robinette Larocque, Lauren Jean Lamb, Na Huang Legden, Henry William Lembeck, Nerjuo Li, Ruolin Li, Brianna Gaujua Lo, Derek James Logan, Joseph Loss, Tyler Dahl Jagger Levrin, Yadi Ma, Xiaowei Ma, Michelle Laura McLennan, Josiah Edward Martinez, Sean Michael McDonough, Cortland Ray McHale, David Cullen McHale, Keegan Patrick McNamara, Liam Richard David Mertz Hoffmeister, Destry James Monk, Brandon Cole Montalvo, Eric Matthew Marin, Togtwen Monks at Seg, Blanca Munoz Perez, Megan Elizabeth Nelson, Brian Charles Nelson, Michael Herbert Neuter, Justin Nikoski, Emmett Nolan Nielsen, Nicholas Vincent Noon, Victoria Catherine Orta, Xinsheng Ouyang, Liu Ouyang, Simon Pasillas, Joshua Pope, Arthur Charles Dennis Pellegrino, Connor Rees Ploy, Jared Popowski, Jonathan Michael Powell, Chu Tse, Adam Edward Reichenbach, Jiao Yuan Ren, Kellen Richard Rice, Hannah Jean Reeder, Noah Chase Rosenthal, Dante Antonio Salas, Paul Schmidt, Erica Schmizer, Alexandra Hope Schwein, Lucas James Simon, Erin Isabella Smith, Yiding Song, Yarrow J. Sullivan, Christopher Irving Thompson, Jade Van Ostel, John Randall Vanderdusen, Fernando Villalobos, Chetan Walia, Megan Elizabeth Walters, Yangdi Wei, Manru Wei, Allison Michelle Weinberger, Megan Grace Wetstein, Benjamin Wilder, Benjamin Reed Wilking, Maxwell Grimes Williams, Richard James Williams, Chen Wu, Dongyu Wu, Yujing Xie, Luiying Zhang, Qingyu Zhang, Bohao Zhang, Kaiyuan Zhang, Miao Zhang, Xu Zhang, Kixan Chu, Maximilian Julius Zim,
Well, our virtual commencement ceremony comes to an end. But before we finish it, there is still one thing which remains to be done. Please move your virtual or real tassels from right to left. And congratulations, class of 2020. You are now CU alumni and forever buffs. Now go to the world and make a difference. Congratulations.
you.